Dynamic programming is a mathematical optimization technique and a computer programming technique invented by Richard Bellman back in the 1950s. He was working for a company called RAND that was contracted to the Department of Defense and used the term to better sell the technique to the Department of Defense, who was a little bit reticent to invest in mathematical research at the time. We've seen a couple different techniques for solving complex problems. One is stepwise refinement or top-down design, functional decomposition, and has a variety of names. Basically, we're breaking a complex problem down into atomic tasks and then writing functions to solve those individual tasks. This has been a handy technique for us throughout CS 150 and into CS 151. The second is recursion, which is finding a solution to a difficult problem by finding solutions to smaller instances of the same problem. Dynamic programming is related to recursion, and it solves a complex problem by breaking it down into a collection of simpler subproblems, finding the optimal solution to each of the subproblems, and then using those solutions to give the optimal solution to the larger problem. Dynamic programming is useful for problems where a naive approach would take exponential time. Dynamic programming, in contrast, typically solves problems in O of n squared or O of n cubed times. It works a bit like recursion, but it involves storing the results to smaller problems so you don't have to go back and calculate them each time. In order to work, dynamic programming needs overlapping subproblems, particularly when the solutions of the same subproblems are needed over and over. It also needs optimal substructure, so the optimal solution of a given problem can be obtained by using the optimal solutions of the subproblems. There are two approaches to dynamic programming, memoization and tabulation. Let's take a look at these. Memoization is a top-down approach and similar to the recursive version of a problem solution. Here, we check a lookup table before computing solutions. We basically set a lookup array with all initial values equal to null. Whenever we need a solution to a subproblem, we first check in lookup table. If it's there, we just simply return it, but if the pre-computed value is not there, then we have to calculate the value and put the result in lookup table so that it can be reused later. In contrast, tabulation is a bottom-up approach. Basically, we build a table in a bottom-up fashion and return the last entry from the table. For example, for the same Fibonacci number that we want to calculate, we calculate fib 0, fib 1, fib 2, fib 3, and so on, all the way up to the one we want, and then put those into the table. So it builds the solution of the subproblems from the bottom up. Here's an example of how we calculate the fifth Fibonacci number. Now here you can see that using the recursive version of the problem calculates f of 4 plus f of 3. In order to get f of 4, we need to add f of 3 plus f of 2. And there's a tremendous amount of work, and in fact we're repeating a tremendous amount of work. And if you look at f of 2, we're calculating that 3 times. Here's a memoization approach to finding the Fibonacci number. We basically begin by looking up and seeing if the Fibonacci number is in the table. If it's not in the table, then we go ahead and calculate it. For the first two, the base cases, that's pretty easy. And then we just use the recursive version for the lookup for any other one. If it's already there, then we simply return it. In contrast, this is a tabulation approach to finding the Fibonacci number. We begin by building a table in a bottom-up fashion and return the last entry from the table. So we basically build the solution of the subproblems from the bottom up and use those previous solutions to calculate the one that we're currently interested in. These are the results of the little experiment that I ran for calculating the 40th Fibonacci number. The recursive took 0.84 seconds, which is darn near an eternity in computer time. You can see the memoization and tabulation gave a lot greater speed up. The times were slightly longer in Visual Studio, but the real factor here was the different type of algorithm that was being used. Dynamic programming has a large number of uses, and I would encourage you to explore these uses. They're particularly handy if you're doing programming contest problems. Longest common subsequence, dynamic programming is applicable to that. Knapsack problem, longest increasing subsequence, it's definitely applicable there. Count numbers with a given digit sum, longest dividing subsequence, and a whole bunch more. Take a look at this technique. It's very useful. Well, that's it for a very quick overview of dynamic programming. Keep up the hard work, and remember this is a great tool to have in your programming toolbox.